Okay, here we go with G9B basic antennas. What's one disadvantage of a directly fed random wire antenna? Now what they're talking about here is just a random length of wire that you throw out into a tree or something like that and connect it directly to your transmitter. Okay, when you do that, you've given no consideration at all to how the length of the antenna relates to the frequency you're going to use. And you're probably going to experience some RF burns when touching metal objects in your station. You're going to have a lot of SWR. You're going to have some high voltages on your equipment. You may even damage your equipment if you do that. So you can't, this works for receivers, but it doesn't work for transmitters. You may, because you'll get a lot of the energy from your transmitter back. What's an advantage of downward sloping radials on a quarter wave ground plane antenna? They bring the feed point impedance closer to 50 ohms. And you remember that we use, that most of our transmitters are designed to feed 50 ohms. We use 50 ohm cable. So if we can bring the antenna impedance to 50 ohms, then that's a good thing. So by sloping these ground radials down instead of straight out, we bring that feed point impedance closer to 50 ohms. What happens to the feed point impedance of a ground plane antenna when its radials are changed from horizontal to downward sloping? It increases. Same picture as before with the radials horizontal. The feed point impedance is approximately 30 ohms. As you bring them down, it increases the impedance until you get to 50 ohms, and that's where you like it. What is the low angle azimuthal radiation pattern of an ideal half-wave dipole antenna installed half wavelength high and parallel to the Earth? This is a real wordy question. What they're basically asking you here is what is the radiation pattern for a dipole antenna, and it's a figure 8 at right angles to the antenna. Looks something like this. Here's the antenna, and here's the power being radiated off of the antenna. This would be looking down on the antenna. Here's the antenna, and you have a figure 8 at right angles to the antenna. How does antenna height affect the horizontal azimuthal radiation pattern of a horizontal dipole antenna? If the antenna is less than a half wavelength high or half wavelength above the ground, the azimuthal pattern is almost omnidirectional. So that directional pattern that we saw in the last slide is lost if your antenna is less than a half wavelength above the ground. It becomes almost omnidirectional, almost the same in all directions. Where should the radial wires of a ground-mounted vertical antenna system be placed? Ground-mounted vertical antenna system. Okay? They should be placed on the surface or buried a few inches below the ground. Now let me show you a picture of an antenna that is just a few miles from me here on the Big Island. I hope you can see that. It's showing up well on my screen. This is the highway right here. This is a vertical antenna that's owned by the Coast Guard, and all of these lines that you see here radiating out away from that are part of the ground system, of the radials, the ground radials for that antenna. And I haven't actually been there and walked on it, but I'm guessing those are buried just a few inches below the surface of the ground. All of those. So it's a ground system for a ground-mounted radio antenna can be quite extensive. This is, incidentally, this is a Google Earth shot, so this shows from space. How does the feed point impedance of a half-wave dipole antenna change as the antenna is lowered from a quarter wave above the ground? it steadily decreases. The feed point impedance of a half-wave dipole, it changes, steadily decreases as you get closer to the ground. Remember I said that a dipole antenna has a characteristic impedance of 75 ohms when it's in free space, but we never get them into free space. About the closest we get with them is a half-wave above the ground, and as we move it down, it steadily decreases. So here we have an antenna that in free space would be a 75 ohm antenna, but as we move it closer to the ground, we use the 50 ohm coaxial cables because they match better for a lower antenna. How does the feed point impedance of a half-wave dipole change as the feed point location is moved from the center toward the ends? As you move the feed point from the center of the antenna, and they're not showing, there's some missing things that would make this clearer. There should be an insulator here. There should be an insulator here. This is your antenna wire here, okay? And here we have moved the feed point from the center right here. We've moved it along the wire until the split now, instead of half and half, is now 2/3 and 1/3. And as we move it away from the center toward the end, the feed point impedance increases, okay? It increases. Now, this is actually an antenna design called a Wyndham, and at this point where you have 2/3 of the wire on one side, 1/3 of the wire on the other side, the feed point impedance has gone up to about 200 ohms. And because it's gone up to about 200 ohms, and we really want to work with 50 ohm cable, we have, and I had a twitchy finger there. Let's go back. Because we have a feed point impedance now of 200 ohms, and because we want to work with 50 ohm cable, we put in a balun here, a 4-to-1 balun, that will cause an impedance transformation from the 200 to the 50 for the feed line. Okay? And this is an actual antenna design called a window, where the feed point is 2/3 of the end of from the wire and 1/3 from the other end, with the feed point impedance being 200 ohms. Which of the following is an advantage of a horizontally polarized compared to a vertically polarized HF antenna? The difference is that there are lower ground reflection losses. You have an advantage that you have lower ground reflection losses. There's an incredible amount of stuff going on in antenna systems. Just absolutely incredible. A lot of it is completely unpredictable. You put the antenna up, you try it. If you like what it does, you leave it alone. If you don't like what it does, you mess with it. And that's one of the big technical fun things of ham radio, is messing with antennas. They're very unpredictable, and if you get a good one, be happy. If you want to improve it, tweak it a little bit, make good measurements, keep good records. But they're extremely unpredictable. They depend on things like what the ground under your antenna is like, how high it is above the ground, all kinds of things. But one of the advantages of horizontally polarized as compared to vertically polarized is you have lower ground reflection losses. What's the approximate length of a half-wave dipole antenna cut for 14.250 megahertz? Okay, the answer to the approximate length for a half-wave dipole antenna cut for 14.250 megahertz is 32 feet. We get that using this formula for half-wave antenna length, the length in feet, 468 divided by the frequency in megahertz. If we take 468 divided by 14.250, we get a length of 32 feet. So this is a good number to know, both for the test and also for the just for making antennas. What's the approximate length for a half-wave dipole antenna cut for 3.550 megahertz? Again, we're going to take the 468 divided by 3.55. We're going to get an antenna length, half-wave antenna length of 131 feet. What's the approximate length for a quarter wave vertical antenna cut for 28.5 megahertz? Well, if the formula for a half wave antenna is 468 divided by the frequency, what do you think the frequency, the formula might be for a quarter wave? It's half of the 468, or 234 divided by the frequency. So when we divide 28.5 into 234, we get 8 feet as the length for our quarter wave vertical antenna for 28.5 megahertz.